Okay, so on to section 4.6. We'll wrap up our conversation about complex numbers and how they interact with polynomials in this section. So the plan is we'll use the conjugate pairs theorem. We'll find polynomials with given zeros and real coefficients in most cases, and we'll find complex zeros of the polynomial. Really, all we have for the complex zeros stuff is the quadratic equation, and that's sufficient, the quadratic formula, and that's sufficient for our purposes, assuming we start with polynomials with real coefficients. We'll state the fundamental theorem of algebra, but not give a proof of it, but we will give a detailed explanation of why we ain't seeing a proof of it. A proof of the fundamental theorem of algebra is most involved. So first, a definition, this time of a polynomial function with complex coefficients. A variable in the complex number system is referred to as a complex variable, commonly denoted with a z. So I denote this as f of z in most settings. In this book, they're going to stick with x as the variable throughout, so we'll do that in the notes too. A complex polynomial function f of degree n is a function of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 and so forth, down to an x term and a constant term. This time, all those coefficients are complex numbers. In the past, we had only considered the case where the coefficients were real numbers. So this is the new part right here. We'll also require a sub n to be non-zero, so this first term isn't zero. And in fact, n is the highest power of x, and so n is the degree of the polynomial. A sub n is called a leading coefficient, and a complex number r such that f of r equals 0 is called a complex zero of the polynomial function. So we've dealt with real zeros, now we're dealing with complex zeros and dealing with, at least in passing, polynomial functions with complex coefficients. Now, there's several versions of the statement of the fundamental theorem of algebra. I'm going to go through a little list of notes I have online for some other classes that deal with the fundamental theorem of algebra and some proofs of the fundamental theorem of algebra. A little presentation, the fundamental theorem of algebra and its history. Go to the online notes, click on the link there. That'll take you to a sort of a story of the historical development of the fundamental theorem of algebra, the ideas of finding zeros of polynomials, some problems with proofs of the fundamental theorem of algebra are addressed in this presentation. A more sort of geometric or visual presentation that gives an intuitive argument for the fundamental theorem of algebra. It's also available in a PowerPoint presentation from a seminar I gave at some point along the lines. It gives you a feeling for why the fundamental theorem of algebra would be the case. And it's based, as is all good proofs of the fundamental theorem of algebra, it's largely based on some theory of complex numbers. Any proof of the fundamental theorem of algebra requires a rather extensive math background. So in the following list are some places where we prove the fundamental theorem of algebra. All of these are either senior level or graduate level classes. That's the necessary evil where you can find a good, clean proof of the fundamental theorem of algebra. And the ones that actually are easy to follow are based on arguments from the realm of complex variables or complex analysis. In our senior level class, complex variables, a cross-listed undergraduate, graduate level class, we use something called Liouville's theorem. Liouville's theorem is used to give actually a relatively easy proof of the fundamental theorem of algebra. Of course, the problem is, where does Liouville's theorem come from? And that's where the extensive math background is. But follow the link, and that will take you to some notes for this complex variables class and give a proof of the fundamental theorem of algebra. In the graduate level complex analysis class, with basically the same proof of the fundamental theorem of algebra is presented there based on Liouville's theorem. Now, here's something weird. In our senior graduate level introduction to modern algebra class, the proof they give of the fundamental theorem of algebra, it's in a section on algebraic extensions. There's a link in the notes to that as well. The proof presented in there also is based on Liouville's theorem. Now, that's kind of awkward and out of place in a class on algebra to drag in this idea of Liouville's theorem, which has quite a deal of background related to the theory of analytic functions from a complex variable. But anyhow, the proof, if you will accept Liouville's theorem, the proof of the fundamental theorem of algebra is very straightforward and very easy. And that's the reason. That's even the proof that's given in the textbook that I like to use for senior level algebra. In graduate level complex analysis, more proofs of the fundamental theorem of algebra given. Proof based on Rouché's theorem, which is based on the argument principle. Never mind what these things mean at this stage, but there's proofs presented online of these, and these are even more ways to prove the fundamental theorem of algebra. So the fundamental theorem of algebra has gotten plenty of attention over the centuries. In Introduction to Topology, a senior graduate level topology class, path homotopies and fundamental groups of surfaces are used to give a proof of the fundamental theorem of algebra. This proof is actually somewhat related to the intuitive presentation that I mentioned before, though the math is all clean and rigorous here and requires a good deal of background. In graduate modern algebra 2, the most advanced algebra class we have at ETSU, a mostly algebraic proof is given. But still, it requires some analysis ideas. It requires the fact that every positive real number has a positive square root, something you might take for granted. But if we were to go through and establish that in a clean, mathematically rigorous way, that requires some concept of what a continuum is. That requires some concept of some of the analysis properties of the real numbers. It also requires that every polynomial of odd degree with real coefficients has a real root. You give me those two results from outside of what's traditionally referred to as algebra, and based on that, we can produce an otherwise purely algebraic proof of the fundamental theorem of algebra. And this idea that a polynomial of odd degree has a root, real coefficients, we've mentioned that before. Our theorem 4.5.h dealt with that. If we have an odd degree polynomial with real coefficients, then on one side it goes up and on the other side it goes down. Some argument about like an end behavior model. Well, if it's positive on one side and negative on the other, or the other way around, somewhere in between it must be zero. That is, somewhere in between it must have a real root. That's the crude argument for theorem 4.5.h in this claim, part B here. But that's based on the intermediate value theorem from calculus. It's based on something that's not purely algebraic and something that's analytic. But the most algebraic proof of the fundamental theorem of algebra accepts these two claims, which can be established in an analysis setting, but not in an algebraic setting. And assuming those, a proof of the fundamental theorem of algebra can be given. I've got online notes from this graduate level algebra class, so help yourself. It's pretty intense stuff. This is the kind of proof that would come at the very end of a year-long graduate-only algebra sequence. So the proof of the fundamental theorem of algebra can be way involved. The easy proof is based on Liouville's theorem, but that's not really an algebraic proof. But if you'll accept Liouville's theorem, then straightforward proof of the fundamental theorem of algebra. And you develop Liouville's theorem in this senior level complex variables class. So that's the quick way to get to a proof of the fundamental theorem of algebra. The fundamental theorem of algebra, little history, was first proved by Carl Friedrich Gauss around 1800. And he gave several proofs of it as well. It's as if he weren't quite satisfied each time he presented a proof of the fundamental theorem of algebra. Later, he'd come back and give another proof of it. Gauss's problem is he didn't know Liouville's theorem. Liouville's theorem is the easy way to get a proof. Liouville works in the mid-1800s, so it's after Gauss has done his work and after Gauss has died. Gauss dies, I think, in about 1840. So there's some history on the fundamental theorem of algebra. Let's get back to our book's presentation and state the fundamental theorem of algebra as it's stated in our textbook. I'll refer to it as Theorem 4.6.a. The fundamental theorem of algebra says, for our purposes, every complex polynomial function f of degree n, at least one, has at least one complex zero. There's one statement of it. We'll give some other statements of it as well. We won't prove it for reasons just explained. A proof of this is far too involved for this level of class. But we'll take the fundamental theorem of algebra in this statement as given, and another statement, Theorem 4.6.b, sometimes this is called the fundamental theorem of algebra. This we can prove using Theorem 4.6.a, accepting this version of the fundamental theorem of algebra and using the knowledge we have, mainly the factor theorem, of the behavior of polynomials, we can demonstrate this version. This says every complex polynomial f of degree n greater than or equal to 1 can be factored into n linear factors, not necessarily distinct factors. Something of the form f of x equals x sub n times x minus r1 times x minus r2, blah, 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 up through x minus r sub n, where a sub n and all these subscripted r's, they're all complex numbers. The coefficients are complex and the roots are complex. Now, when I say complex number, the complex numbers include the real numbers. So these r's, they could be complex numbers, including the fact that they could be real numbers. And the examples we'll see will involve some real numbers and some complex numbers, some non-real complex numbers. So what we're getting here really is every complex polynomial of degree n greater than or equal to 1 has exactly n complex zeros, some of which may be repeated. Those zeros are r1, r2, up through r sub n. The fundamental theorem of algebra stated here says every n degree polynomial has at least one complex zero. This says an n degree polynomial has really exactly n zeros if we count multiplicity. So there's how the books balance, and we get the same number of zeros as we have the degree of the polynomial. It can also be expressed in some type of factoring situation, which is how it's presented in Theorem 4.6.b. Let's go through a proof of Theorem 4.6.b. Okay, so claim is every complex polynomial function f of degree n greater than or equal to 1 can be factored like this, using complex numbers as explained. All right, so start with f of x is given, n degree polynomial with complex coefficients, accepting the fundamental theorem of algebra as we stated it, f has at least one zero. Let's call it r sub 1. Now, the factor theorem tells us that finding zeros of a polynomial is equivalent to finding linear factors, finding factors of the form x minus r1. So if r1 is a zero of this polynomial, or a root of this polynomial equation, then by the factor theorem, x minus r sub 1 is a factor of this polynomial. In other words, f of x can be factored into x minus r1 times q1 of x, where q1 of x is some polynomial, and the degree of the q1 polynomial will be n minus 1. The leading coefficient of the q1 polynomial will be a sub n, so that when we multiply this out, we still get the first term as a sub n x to the n. So we're going to see this a sub n term appear after we factored it as well. So r1 is a root, or 0 of the polynomial. Then x minus r1 is a factor. Factor it out, produce this quotient, that's the symbol q sub 1 of x, an n minus 1 degree polynomial. Hey, by the fundamental theorem of algebra, theorem 4.6.a, then q1 has some root, r sub 2. So what we're going to do is repeat this argument. Strictly speaking, we're using something called mathematical induction. It's explained later in the book. But there's an r sub 2 that's a root of q sub 1. And so we can factor q sub 1 as x minus r sub 2 times a q sub 3. Hey, q sub 3 has a root, r sub 3. So we can factor out an x minus r sub 3, continue this process. So we're doing something inductive. After we've done this n times, remember, the degree of this quotient polynomial decreases by 1 each time we pull a factor out. So after n iterations, we've produced these n roots. We started with a polynomial f of degree n. After n linear factors have been pulled out, the degree of the quotient q is reduced by n. And so we get this q sub n complex polynomial has degree n minus n, has degree 0. It's a constant term. Each time the leading coefficient in those quotient polynomials had to be a sub n, and that's the case in this quotient polynomial as well. It's a constant, and that constant is a sub n. As you can see, if we'll take a sub n times all of these factors, when you multiply all this out, the leading term will be a sub n x to the n power. Multiply all the x's together, produces an x to the n and an a sub n coefficient. And that's the kind of behavior that we wanted if we'll look back at the original statement of the polynomial function. A sub n x to the n was the leading term. So we've got f of x factored in this form. Each of these are linear factors. There are n of them. Nothing stopped us from having, for example, r1 and r2 are the same. So these are not necessarily distinct factors. It could be, say, we've actually got x minus r1 squared for all we know. There could be repetitions in the roots. And so there could be repetitions in these linear factors, which would lead us to discuss zeros of a certain multiplicity, as we've done in the past. Returning to the notes, the following theorem is related to our theorem 4.5.g from the previous section, which stated every polynomial function with real coefficients can be uniquely factored into a product of linear factors and or irreducible quadratic factors. So slightly different setting from what we're talking about in this section. We're reverting back to section 4.5, and there we considered real coefficients, polynomials with real coefficients. And what we stated without proof, we didn't have the equipment to prove it in the previous section, but we're about to have the equipment. And we'll give a proof of this. If the polynomial has real coefficients, you can't necessarily factor it into a bunch of linear terms, but you can factor it into linear terms and irreducible quadratic terms. The setting of theorem 4.5 is only using real numbers. Theorem 4.6 allowed complex stuff all over the place. Complex coefficients, complex roots, all that was on the table in theorem 4.6.b and also in the fundamental theorem of algebra. But theorem 4.5.g deals with only polynomials with real coefficients and only considers real zeros of that polynomial. And those real zeros will be associated with real linear factors, it turns out. In the direction of the proof, theorem 4.6.c is called the conjugate pairs theorem and says, let f be a polynomial function with coefficients that are real numbers if r equals a plus bi is a zero of this polynomial function with real coefficients. Then the complex conjugate, r conjugate, a little typo there that should read r conjugate, equals a minus bi is also a zero of the function. So if a plus bi is a zero, then a minus bi is also a zero of a polynomial with real coefficients. Let's look at the proof of that. This one actually is pretty easy. I need to appeal to your knowledge of the behavior of conjugates, something we covered in one of the appendices. So suppose f of x is a polynomial function with real coefficients. If r equals a plus bi is a zero of f, that means f of r, f of a plus bi equals 0. So we're supposing that's a 0, and we're trying to show the conjugate of that is also a 0. But assuming f of r equals 0, we'll simply plug r in. That produces this. R is representing a plus bi. We'll deal with the substitutions later. By properties of the conjugate, in particular, this is spelled out in Appendix 7 in Theorem A.7.A. In the notes, there's a link to that. We know the following. So we've got this equals 0. If the two numbers are equal, the two complex numbers are equal, then we can conjugate both sides. If they're equal, their conjugates are equal. The conjugate of a sum is the sum of the conjugates. So we've taken this conjugation and in some sense distributed it over the addition sign and put it on each of the constituent terms in this sum. The conjugate of the product is the product of the conjugates. So here we've got the conjugate of a sub n times r to the n. That would be the conjugate of a sub n times the conjugate of r to the n, which in turn, repeatedly applying properties of the conjugate, that the conjugate of the product is the product of the conjugates, allows us to write that as r conjugate to the n. So we're repeatedly using the fact that the conjugate of a product is the product of a conjugate. And that produces all these conjugates and these r conjugate to the n powers, and r conjugate to the n minus 1 down to r conjugate to the first power. All right, so properties of conjugates takes us to this point. Conjugation was when we simply took a complex number and replaced the imaginary part with its negative. Definition of conjugation. So if you conjugate a real number for which the imaginary part is 0, nothing happens. So this conjugation idea is new to you unless you've dealt with complex numbers before. It's not something you talk about in the setting of real numbers. But we got some real numbers here. All the coefficients were real numbers. All the a sub n minus 1 coefficients, those are all real numbers. So when we conjugate all these coefficients, nothing happens because those coefficients are real numbers. 0 is a real number. When we conjugate 0, nothing happens. In other words, a sub n conjugate is a sub n. A sub n minus 1 conjugate is a sub n minus 1. A sub 0 conjugate is a sub 0. 0 conjugate is 0 itself. Because all of these things are real numbers. Now, what we've got here is the f of x function with r bar substituted in. So the left-hand side of this equation is f of r bar, f of the conjugate of r. And the right-hand side simply 0. So we have f of r conjugate equals 0. So r conjugate is also a 0 of the function. You plug r conjugate into the function, you get 0 out. If a plus bi is a 0 of f, a minus bi is a 0 of f as well. assuming again, f is a polynomial function with real coefficients. And right here is where we were heavily dependent on the real coefficients part. A little comment in the notes about these, an implication of what happens from having this conjugate behavior. The irreducible quadratics of a real polynomial function, this existing by, again, theorem 4.5.g, every polynomial function with real coefficients can be uniquely factored into a product of linear factors and irreducible quadratics. About those irreducible quadratics, they correspond to this behavior of complex conjugate pairs of roots of a real polynomial function. For example, we saw if a plus bi was a root of such a polynomial function, or 0 is such a polynomial function, then so is a minus bi. If a plus bi is a 0 of that function, then x minus a plus bi is a factor. Factor theorem tells us that. Similarly for the a minus bi. If a minus bi is 0 of the polynomial function, then x minus a minus bi is a factor. So we get these two linear factors associated with these two zeros, a plus bi and a minus bi. Let's see what happens when we multiply those together. Distribute, it's a little complicated. We've actually got 3 terms here when I distribute the negative signs, but follow your nose, do the distribution, collect the terms together, and those two linear terms yield this quadratic. This is x squared minus 2ax plus a squared plus b squared. Notice all the i's are gone. And if you'll distribute and multiply out, you'll see where they went to. There was some cancellation and an I squared producing a -1 somewhere in there. But we get this second degree quadratic, and this is irreducible. We'll discuss this here downstream in a little while, but this is an irreducible quadratic over the real numbers. If you restrict it to real numbers, you cannot factor this. If you use complex numbers, you can factor it. There's how it factors right there. That's where it came from. But the irreducible quadratics of theorem 4.5.g are associated with conjugate pairs of zeros that are guaranteed to exist by the conjugate pairs theorem. So the reason these irreducible quadratics are irreducible is because the two zeros that they do have, they're complex. And in theorem 4.5, we were only dealing with real numbers. Remember, it's the previous section, and complex numbers were off the table in that section. So the next result, which is equivalent to our theorem 4.5.h stated previously, we can prove this now using the conjugate pairs theorem. This says a polynomial function f of odd degree with real coefficients has at least one zero. Polynomial function, real coefficients, right, it comes out of section 4.5 where everything was real, has at least one real zero. Remember, odd degree means it goes up on one side and down on the other, or up on the other and down on the one. Anyhow, it goes up on one side and down on the other side. Odd degree polynomials will behave like that. You plug in big positive numbers and you plug in big negative numbers, you'll get out either big positive numbers or big negative numbers, maybe not respectively. But far to the right and far to the left, you got opposite signs of output of the function. Polynomial functions are continuous, an analytic concept. Well, if they're continuous and positive in one place and negative in another, they had to be zero somewhere in between. This was our argument for this before. Now we can establish this using the conjugate pairs theorem. So here's the claim. The proof simply argues in terms of the factoring of that function. Complex zeros occur in conjugate pairs for polynomial function. as we saw, and that's how we get the irreducible quadratics. That was the conjugate pairs theorem. So there will always be an even number of zeros that are not real numbers. The not real zeros of the polynomial function, they always come in conjugate pairs. So if you got one, there's another one paired with it out there. So when we count up the number of non-real zeros of a polynomial function with real coefficients, that'll be an even number. But remember, an odd degree polynomial will have a total of an odd number of zeros. Well, it's got an even number of those zeros that are not real. That leaves over at least one zero that must be real, and possibly more, as we'll see by examples in some of the future. But there's got to be at least one root, 1 0 of that polynomial that is not a complex number that's unreal. There's got to be a real root left over. The complex numbers, the purely complex numbers, come in conjugate pairs. So it's an even oddness argument when we dissect it in more detail. Let's do a couple of examples, 16 and 22 from the section. Oops. Okay, here they ask us to find a polynomial with certain properties. Suppose polynomial function f with real coefficients is of degree 6 and has zeros I, 3 minus 2i, negative 2 plus I. Find the remaining zeros. The real key feature is f has real coefficients. Well, if it's got real coefficients and it has these three complex roots, then it must have as roots also, as zeros of the function also, their conjugates. We know that by the conjugate pairs theorem. For any complex number r, a zero of a polynomial function with real coefficients, the conjugate is also a zero of that function. So if we take r1 equals to I, r2 equals to the second one, 3 minus 2i, and r3 equals negative 2 plus I. These are zeros of f, they told us that, so their conjugates must also be zeros. R1 conjugate, that'd be I conjugate. Put a negative in front of the imaginary part, which is simply 1, so we get negative 1i. Here, change the sign on the coefficient of the imaginary part from negative to positive when you do the conjugation. Negative 2 plus I, change the sign on the imaginary part. Plus I becomes a minus I. These three conjugates have to also be zeros. Now, that gives us 6 numbers that are zeros of that polynomial function. We were told they want a degree 6 polynomial function. F is degree 6. Well, it can only have as many zeros as the degree by the fundamental theorem of algebra. So the 6 zeros we're aware of must be all of the zeros of the polynomial function. The 3 they gave us, they wanted us to find the remaining ones. Well, the remaining ones are the conjugates of the 3 given ones, and there's the reasons why. Again, only valid. This is only working because we're dealing with a polynomial function with real coefficients. Number 22, find a polynomial function f with real coefficients having degree 5 and the zeros 1 of multiplicity 3 and 1 plus I. Answers will vary depending on the choice of the leading coefficient. Okay. All right. F has real coefficients, conjugate pairs theorem. Same argument as in the previous example. For any complex 0 r of f, r bar, our conjugate, is also a 0 of f. Well, we were told 1 plus I, let's denote that as r, is a 0 of f. So its conjugate, 1 minus I, is also a 0. That takes care of the complex information we were given. We're told 1 is a 0 of multiplicity 3. We're told f is of degree 5. We've got 5 zeros counting multiplicity. We've got 0, 1 of multiplicity 3. We've got the 1 plus I 0 that they gave us, and the 1 plus I conjugate, the 1 minus I 0. So there's 5 zeros right there counting multiplicity. So by the fundamental theorem of algebra, degree 5 polynomial has exactly 5 zeros if we use complex numbers. And we found those 5 zeros. They are, again, 1, 1, 1, 1 plus I, and 1 minus I. So the 1 has to count 3 times. We know by the factor theorem for the 0 of 1, we have associated with that a factor of x minus 1, 3 times. For the 0 of 1 plus I that they gave us, we have the factor x minus 1 plus I. From the 0, 1 minus I that we figured out, based on the conjugate pairs theorem, we have the factor x minus 1 minus I. So here's 5 factors, and these are the only linear factors of this polynomial function. We'll multiply them all together, we'll get a 5th degree polynomial. So let's take x minus 1 times x minus 1 times x minus 1, x minus 1 cubed times these other 2 factors. If you like, we can multiply out here. We illustrated this in terms of A's and B's in the notes. But if you will distribute and do the multiplication, you'll get x squared minus 2x plus 2. This is an x minus something times x. I was looking for a special kind of pairing. I guess it isn't so much. It's an x minus complex number times x minus its conjugate. I guess that's what's special about it. The modulus of 1 minus I and 1 plus I is 2. That's not a coincidence. But if you'll distribute out, you'll see that it simplifies to this. If you wish to factor it and express it in terms of real numbers, that's sort of the spirit of the question. They ask us to find a polynomial function with real coefficients, so we do have to multiply out. So this will have exactly the zeros we wanted. This will have 1 3 times as a 0. It'll have 1 plus I as a 0. And we knew that it had to have the 1 minus I because of their demand to have real coefficients. So this polynomial will work. We could take f of x to be this polynomial, and it's got real coefficients. Multiply it out if you're so obsessed. Indeed, we'll have a 5th degree polynomial. But this 5th degree polynomial has all of the appropriate roots. I'll take that as our answer. They said something about answers will vary depending on the choice of the leading coefficient. We could take that and multiply it by something other than 0, so multiply by 7. And if you just put a leading coefficient out here, as long as it ain't 0, you'll have the same zeros and a different polynomial function. So that's their comment about answers will vary depending on the leading coefficient. Multiply the whole thing by 51, and it's still got the same zeros, and it's a different polynomial function. Okay, said I owe you a proof of theorem 4.5.g, so let's do that, followed by a final example. We got the equipment to prove theorem 4.5.g. Again, that said every polynomial function with real coefficients. Actually, they didn't put that part in the statement of it, I don't think, in section 4.5. That was the understanding that we were dealing with real numbers in that section, but not anymore. So let me make it explicit. Every polynomial function with real coefficients can be uniquely factored into a product of linear factors and or irreducible quadratic factors. This you will see again in Calculus 2 when you do something called integration using partial fractions. The reason this is true, we're about to justify, ultimately based on the fundamental theorem of algebra. The things you will do to those functions in Calculus 2 are calculus things, but you need this algebra background to get things set up. All right, so on to a proof of that claim about linear factors and irreducible quadratics, only dealing with polynomial functions of real coefficients. In Calculus 1, 2, and 3, you'll only consider real numbers. You got enough on your plate with a calculus of functions of a real variable. You want to do calculus of functions of a complex variable. That's where that complex variables class comes in. Okay. Every complex polynomial function f of degree n has exactly n zeros, fundamental theorem of algebra, and therefore can be factored into a product of n linear factors by the factor theorem. If its coefficients are real, these zeros that are complex numbers will always occur as conjugate pairs by the conjugate pairs theorem. So if r equals a plus bi is a complex zero, b not equal to 0, so it's not actually a real number, then r conjugate, a plus bi conjugate, that is a minus bi, is also a zero of that complex function. Having real coefficients, any complex zeros come in conjugate pairs. So the linear factors x minus r and x minus r conjugate of f get multiplied together, and we get x minus r times x minus r conjugate. I told you we'd look at this here later. Later is now. If we FOIL this, we'll have an x squared term. We'll have minus rx minus r conjugate x. So here's the x, here's the r and the r conjugate, here's the minus. And then we'll have plus r times r conjugate, r times r conjugate. Ooh, r times r conjugate, see the review section, appendix 8.7 it was. And a complex number times its conjugate yields the modulus squared of that complex number. And that's the reason we're getting this a squared plus b squared stuff. So you might need to review what a conjugate, or I'm sorry, what a modulus of a complex number is. But that's what we get from r times r conjugate. R plus r conjugate is simply adding these two together. The plus bi and the minus bi cancel. The plus bi minus bi cancel here. This, were we to expand it and multiply it out, also a way to see that you get a squared plus b squared. But what will happen there is the only appearance of the I term when you multiply out will be I squared. Well, I squared is -1. And the imaginary stuff has disappeared over here as well. Notice what you get when you multiply these together is a polynomial, a second degree polynomial equation, a quadratic, with only real coefficients. A and B are real, so these coefficients are real. Actually, here's the distribution and showing the simplification down at the bottom. Yeah, when you multiply r times r conjugate, produces this. There's some cancellation with a negative sign, and there's an I squared that produces a -1 to turn this into a plus b squared, as given there. So there's the details on the algebra of that. All right, so the complex zeros of the function are associated in conjugate pairs, and as a result are associated with these types of quadratics. These types of quadratics. Now, these types of quadratics, these are irreducible over the real numbers, because if we were to try to set this equal to 0 and solve for x, we might use a quadratic formula, leading us to consider the discriminant. The discriminant would be, I usually describe it as b squared minus 4ac, but a and b are playing other roles here. So we'll get this thing with a -2a, we'll get that squared, that's b squared in the symbols of the discriminant, minus 4, leading coefficient is 1, constant term, C, is a squared plus b squared. So if we look at the discriminant with these coefficients, that produces this. Let's see, that's 4a squared minus 4a squared minus 4b squared. These two cancel, leaves us with -4b squared, and that's less than 0. Remember, b was non-zero. We were dealing with a non-real root when we looked at the a plus ib stuff, or a plus bi. So the discriminant is negative. That means there are no real roots of this. There's complex roots. In fact, that's where this came from, but there's no real roots. In other words, this is irreducible over the real numbers. Irreducibility depends on where you are. If you won't let me use complex numbers, this is irreducible. If you will let me use complex numbers, I can factor it into a product of two linear terms, and they will involve complex conjugates by the conjugate pairs theorem. So the factors of f are either the linear factors, these are associated with the real zeros of the form x minus real root, or irreducible quadratics, and these are associated with the conjugate pairs, a plus bi and a minus bi, that you know must be the case whenever you deal with a polynomial function with real coefficients. So that's the reason, and that's the proof of why a polynomial function with real coefficients can be factored into a product of linear terms and irreducible quadratics. Why are they irreducible? Because we're stuck on this real coefficients thing so much. They wouldn't be if you let me use complex numbers. We could reduce these quadratics as well. But if you restrict your attention to real coefficients, and you'll do that in calculus, then those quadratics become irreducible. Okay, one final and potentially extremely lengthy example is the following. Find the complex zeros of the polynomial function and write it in factored form. Okay, fourth degree polynomial. We're going to throw sort of a finale of the algebra stuff before we shift gears and start looking at logs and exponential functions in chapter 5. We're going to throw a lot of our background information at this one question. Descartes' rule of signs, Theorem 4.5.e, says count the number of sign changes in the coefficients. Coefficients are 1, positive 3, negative 19, positive 27, negative 252. Here's the coefficients. How many sign changes? Nope. Yes. 1, 2, 3. Changes from positive to negative to positive to negative. There's 3 sign changes in those coefficients. So the number of zeros that are positive and real is either 3 because of the 3 sign changes, or that number less 2 or 1. So it's either 3 or 1, positive real zeros. Again, this is Theorem 4.5.e, Descartes' rule of signs. Telling us, well, there's at least 1. For sure, there's 1 positive real zero, possibly 3. How about negative real zeros? We consider f of negative x. F of negative x, replace x with negative x. The even exponents absorb that negative sign. The odd ones do not. So the 3x cubed up here will become a negative 3x cubed when we make the substitution. The 27x will become a negative 27x when we make the substitution. The other coefficients remain the same, the ones corresponding to even exponents. So this polynomial has coefficients 1, negative 3, negative 10, negative 27, negative 252, and there's only 1 sign change in that one, telling us the original function f has 1 negative real zero, Descartes' rule of signs, or that less by 2, but it's meaningless to have negative 1 zeros. So this function has, for sure, 1 positive real zero and 1 negative real zero. And it might have more positive real zeros for all we know. We got a degree 4 polynomial. We know it has at least 2 real zeros. So here's hopefully what we can do. If we can find those 2 real zeros, then we could divide this 4th degree polynomial by each of the associated linear factors with those 2 real zeros. And that would leave us with 4th degree polynomial divided by a 2nd degree polynomial will leave us with a 2nd degree polynomial. Can you factor a 2nd degree polynomial? Absolutely, using the quadratic formula, as long as it's got real coefficients, for all we know. All right, so the plan is, let's find those two real zeros. Okay, we've got a technique for doing that. The rational zeros theorem that we saw in the previous section. We're going to consider the factors of the leading coefficient. Leading coefficient is 1, a sub 4 equals 1. And the divisors of 1, integer divisors, are plus or minus 1. And we're going to consider the constant term. A sub 0 equals negative 252. And we're going to find all of the divisors of negative 252. And they are plentiful. I think there's 36 numbers listed here. Wow. All right. Well, this is what we have. So didn't promise you a rose garden, but we've got a list of all potential rational zeros. If it doesn't have rational zeros, we probably can't figure this out. It does. We certainly got plenty of opportunities to check here. All right, so what we'll do is take the factors of a sub 0, divide them by the factors of a sub 4. So divide all 36 of these by plus or minus 1. You get the same list of 36 numbers. So we'll go through and check those numbers. Nothing to be learned by all of the failures. We got 36 numbers here. A bunch of them ain't going to work. Omitting many computations, we find 2 of them do work. Positive 4 and negative 7 were on the list. Let me go back. Positive 4 and negative 7. Yeah, those were on the list. And it looks like those 2 work. So by plugging those numbers into the function, we'll find 2 of the real zeros. And notice one of them is positive and the other one's negative, as predicted. None of the other potential zeros are in fact zeros. You go through the other 36 of them and they simply don't work. And that was sort of the problem with the rational zeros technique. It gave you maybe a big long list of potential rational zeros, but a bunch of them probably ain't going to work. So we know by the factor theorem that x minus 4 and x minus negative 7, or x plus 7, both of these are factors of the original function. So if we'll multiply them together, multiply x minus 4 times x plus 7, that's also a factor of f. By the way, that gives us x squared plus 3x minus 28, our old pal FOIL again. As I said, let's do long division. So let's take the original function and divide it by x minus 4 times x plus 7. Divided by this, I need it multiplied out to perform the long division. Trying to eliminate the x to the 4th term, we'll multiply by x squared. That will produce this polynomial. Let me go through the arithmetic part somewhat quickly. We'll subtract. This cancels, this cancels. This subtracting produces a 9x squared, and we'll bring down the other terms. How are you going to eliminate the 9x squared? Let's multiply the divisor by 9, produces this, and in fact, we get a remainder of 0. Is that right? Yeah, we should have got a remainder of 0. Remember, we know this is a factor of the function. It divides it evenly. So the remainder better be 0. So things are falling into place with this. And we had the quotient x squared plus 9. So here's where we stand. F of x is this times that. X squared plus 3x minus 28 times x squared plus 9. In fact, x squared plus 3x minus 28 we know to be x minus 4 times x plus 7. So we've got f of x factored into this form. We just need to find the roots of x squared plus 9, or we need to factor x squared plus 9. Can't do that over the real numbers. X squared plus 9 is irreducible over the real numbers. This is never 0. We get x squared equals negative 9. Never 0 for real numbers. But if you let me use complex numbers, we get 2 solutions. X squared plus 9 equals 0. We could take x to be, in a sense, plus or minus the square root of negative 9, which we can deal with in terms of complex numbers. We get either 3i or negative 3i. Really, I don't want to talk about the complex square root function. That's a very lengthy story in itself, it turns out. But certainly, if you'll take 3i and square it, you'll get 9 times I squared. That's negative 9, and that'll work. And similarly, square this, you'll also get -9. The negative sign's absorbed in the squaring procedure. So both of these are roots of x squared plus 9, zeros of that polynomial function. And so we can factor x squared plus 9 into the product of these two linear terms. So 3i and -3i, these are also zeros of that function. They wanted us to find the complex zeros. Let's go a little further than that. Let's give them all the zeros. The zeros are +4, -7, 3i, and -3i. Fourth degree polynomial, there's the 4 zeros of that polynomial function. And it couldn't have but 4 by the fundamental theorem of algebra. Degree 4 polynomial will have 4 roots, counting multiplicity. They're all multiplicity 1 in this one. You want to factor f. They wanted it in factored form. Okay, fine. We could write it as x minus 4 times x plus 7 times x minus 3i times x plus 3i, using all of the 4 roots that were given here. We could also multiply these together and write it as a product of 2 linear factors and an irreducible quadratic. Irreducible over the real numbers. Remember, these two multiply together to give us x squared plus 9. We had that on the previous slide. So there it is, factored into linear terms using complex zeros. And along the way, we saw linear factors and irreducible quadratics. And that's the story of complex numbers. So if you'll take the material in Appendix A4, along with the material in this section, you've got mostly a standalone discussion of complex numbers and an introduction to complex numbers, though this section did depend moderately on several of the results in section 4.5, the previous section. But that takes care of our exploration of complex numbers. That takes care of at least 3/4 of Precalculus 1. What remains is the Chapter 5 material, and the Chapter 5 material is on log functions and exponential functions. And it's all back to real numbers. The remainder of Precalculus 1 is all real numbers. And Precalculus 2 will probably exclusively deal with real numbers. The complex number stuff was in the Appendix A4 and in this section here. So have a nice day. I'll see you in Chapter 5. Bye-bye.